Watch how one of the toughest Soviet trucks was built, and how robots build its modern successors today. From manual muscle to robotic precision, this is how trucks were made, then and now. Engine testing on early ZIL power plants. Cold, brutal Soviet engineering. Inside the Valdai truck plant. Modern Russian assembly in action. Mercedes off-road trucks. Rugged engineering built for real-world punishment. Daimler trucks, where heavy-duty American freight machines come to life. Chevrolet Silverado HD, born on a high-precision manufacturing line. And so much more. From robotics to next-gen truck tech.
Welcome to the Workshop Guru.
At the Likachev Moscow automobile plant, production of the ZIL-130 begins long before a single tool meets metal. The complex stretches across an industrial district. Massive workshops, interconnected galleries, and multi-level transport bridges forming a single coordinated organism built for scale, precision, and uninterrupted workflow. Every building exists as part of a continuous manufacturing chain, and every movement of material is engineered to fit into the strict rhythm of Soviet automotive production. Outside the main assembly halls, freshly completed ZIL-130s form long rows, cabs uncovered, components exposed, each truck awaiting final inspection or transport. This outward flow reflects the internal structure of the plant, a production rhythm calculated to deliver thousands of vehicles each year. The movement of trucks between buildings highlights a factory designed not as separate workshops, but as a tightly integrated assembly ecosystem. As the camera enters the assembly buildings, the scale becomes clear. Long conveyors stretch across the floor, carrying ZIL frames through an assembly cycle that transforms raw steel into completed vehicles. From this vantage point, overhead lighting and roof trusses reveal the scale of the building, calculated to house full-length conveyor runs without interruption. High above, steel beams support gantries and cranes that feed heavy stampings and rolled sections into the press shops below. Stacks of pre-cut sheet and profile stock are stored in multi-tier racks, arranged so overhead magnets can lift any layer without disturbing the rest. A bundle of steel moves along a suspended carrier. Each motion follows a programmed route that optimizes loading for the large stamping presses. Down the line, side presses form cross members and brackets. Automatic ejectors push finished parts onto roller tables that feed the next station. A conveyor of bare frame rails advances slowly, guided in side channels that keep each piece aligned for drilling, punching, and marking.
Millions were built, and a significant number are still working today, supported by parts availability.
Rotary fixtures keep the rail perfectly vertical, as punches and drills work from multiple sides. Finished frame sections slide onto a mesh table for interim storage. Machined rails are clamped to sliding bases. Locator pins engage the drilled holes, locking geometry for welding of cross members and brackets. A gantry system advances over the jig, carrying automatic welding heads that trace programmed seams along the longitudinal and transverse joints. Safety blocks and bumpers guide the moving frames through stations. We shift to the control room, where brigade leaders monitor the entire press and frame line from a panelized console. Rows of operators sit at these panels, each responsible for a segment of the plant's conveyor network and its corresponding machinery. A senior operator adjusts selector switches and rotary knobs. With a few commands, conveyor speeds and accumulation zones can be rebalanced. The team coordinates startups, stoppages, and line transfers, keeping hundreds of meters of track and dozens of machines in stable, synchronized operation. Outside again, we see the glass-walled body shop, where cab shells and panels are assembled before meeting the rolling chassis. Inside, a suspended body conveyor carries complete cabs over a lower line of chassis, staging them for the body-on-frame marriage operation. Overhead, a row of engines or large sub-assemblies hangs from the monorail. A cab descends toward its frame, guided by adjustable arms. Multiple stations along this elevated line prepare the underbody for mechanical equipment. A freshly assembled rear axle moves along a separate conveyor, its differential housing and brake backing plates already installed. Overhead lifting gear and compressed air tools hang in the background, shared infrastructure used for axle mounting and final undercarriage tasks. Axles are aligned with the frame on jigs. An operator checks positioning against gauges. In this stage, center distance and pinion angle are set to guarantee correct driveline geometry. Visual inspection supplements gauges, as workers verify weld beads, fastener torque marks, and the condition of machined surfaces. Pneumatic tools tighten spring shackles and torque rods. Calibrated pressure regulators ensure every fastener receives the same clamping force. A spiral of hoses overhead supplies air and oil to powered tools. From a distance, we see multiple chassis with bare frames but complete running gear, all synchronized on the same undercarriage conveyor. A swinging manipulator feeds heavy components, fuel tanks, spare wheel carriers, and battery boxes onto the side of the chassis without manual lifting. On the following section, bare frames wait for aggregates. This buffer zone absorbs short disruptions without stopping the entire conveyor loop. Workers prepare mounting surfaces, clean threads, and position engine mounts, ensuring the power unit can be dropped into place without adjustment delays. A fitter watches his station. The engine itself appears, suspended from an overhead hoist. Alignment guides prevent swinging and keep the crankshaft axis parallel to the frame. Two assemblers coordinate the lowering operation, watching reference marks so the engine lands on its rubber mounts without torsional stress. A top view reveals the powertrain in plan. Gearbox, prop shaft connections, and exhaust routing are all laid out for easy access. Close on a worker's hands as he locks flexible fuel and vacuum lines into clamps.
Working long hours on the conveyor is hard. For me.
Preventing chafing once the truck enters service. A line worker at the side of the conveyor connects electrical systems, using test lamps and diagrams to verify each circuit. Inside the cab, a female assembler installs dashboard controls, switches, and wiring looms, securing each connector with mechanical locks. Overhead, the monorail delivers a fully assembled cab shell, complete with front fascia, grille, and headlights installed. Suspended from a rigid lifting frame, the entire cab is lowered in a controlled descent toward the waiting chassis. Workers position themselves around the frame, guiding the approach by hand to ensure alignment with the engine mounts and firewall contact points. A curved overhead rail transports painted wheels and tires. This separate loop keeps heavy rotating parts flowing continuously to the mounting stations. Using an overhead hoist, a worker positions a heavy wheel and brake drum assembly onto the rear axle. An inspector stands beside the line with a checklist, verifying that each fastening point on the newly mounted wheel assembly meets specification. Inside the cab again, upholstery, seat frames, and door panels are mounted. A close-up of a mechanic tightening a component shows attention to manual craft still present alongside automation. The truck moves forward under its own wheels along an internal test lane. A view from below the cab shows pedals, steering column, and control linkages connected, forming the interface between driver and machine. A dedicated bay houses a short rolling road where each truck can be run at speed without leaving the factory building. The rear wheels sit on large rollers. As the truck accelerates, load and speed are measured to verify power transmission and braking performance. Inside the cab, a test driver listens for vibrations and noise. At the end of the hall, an illuminated sign marks the final inspection gate. Only trucks that pass here are cleared for release to the yard. The next stage of the story begins. Inside the engine test stands, where every ZIL power unit proves its strength before it ever turns a wheel on the road. Inside the testing department, engineers review engine specifications, tolerances, and test protocols before mechanical verification begins. Documentation and calculation remain central. Mechanical assemblies are visually checked for correct installation before the engine is connected to diagnostic equipment. Pressure gauges are mounted directly to the engine. Control rooms adjacent to the test cells house analog monitoring equipment. Oscillographs, counters, and recording units. Frequency analyzers track ignition stability and rotational consistency across multiple RPM ranges. Every adjustment is deliberate. Fuel mixture, ignition timing, and airflow are set to standardized factory baselines. From behind reinforced glass, engineers monitor gauges as the engine is brought up to operating temperature. The engine runs under sustained load, simulating real-world operating stress without vehicle movement. Technicians adjust control levers, increasing rotational speed in controlled increments. A large analog scale registers torque output, confirming power delivery meets design targets. The V8 engine maintains steady combustion, exhaust routing visible as heat builds across the system. Fuel delivery lines are checked for pressure consistency during prolonged operation. Engine noise, knock, and irregular combustion are detected by trained technicians, not electronic filters. Engine blocks are inspected for oil seepage or thermal deformation during peak load. Electronic and mechanical recording systems archive the engine's performance signature. Each tested engine is classified, approved, adjusted, or returned for correction. This stage ensures failures are eliminated before reaching the production line. This discipline reflects an era where mechanical trust was built through measurement. From test benches, the focus now shifts back to mass production. Next, we move forward in time, examining how the UAZ production line reshaped Russian vehicle manufacturing from the Soviet era to today. Inside the UAZ plant, a new production hall is commissioned around heavy robotic infrastructure. Overhead bridge cranes span the workshop, designed to position press modules with millimeter accuracy. Structural frames are anchored into reinforced foundations, forming the base of a high-tonnage stamping system. Here, a 1,000-ton press complex is installed to handle large automotive body panels. The press line is configured for continuous operation, minimizing manual intervention. Each press station is aligned to accept automated material feed from robotic handling systems. This line is designed to stamp body components for Sollers pickups and SUV platforms. 6 industrial robots replace manual transfer between press stages. The entire process is controlled from a single operator station. Human supervision shifts from physical labor to process monitoring and system diagnostics. From conveyor-driven Soviet lines to robotic cells, the logic of manufacturing evolves. The UAZ production line begins with a rigid positioning table. The body shell is fixed in a calibrated coordinate system. Laser-guided measuring arms define reference points. Dimensional control replaces visual judgment. An operator monitors geometry from a digital terminal. Corrections are applied before assembly advances. Probing heads scan panel edges and mounting zones. Tolerance is verified in real time. Here, accuracy is achieved before force is applied. This is preventive engineering, not correction. Manual tools are still present, but they serve measurement, not alignment. Parallel to body assembly, engine blocks enter a separate machining cell. Processes are isolated but synchronized. Raw castings are clamped into CNC fixtures. Positioning is automatic and repeatable. Crankshaft journals are machined under enclosure. Robotic transfer arms move blocks between stations. Inspection cameras verify surface finish. Finished blocks exit machining cells in uniform condition. Valve seats and ports are CNC-shaped. This contrasts sharply with ZIL-era manual machining. Here, consistency replaces craftsmanship. Blocks and heads converge only after independent verification. Subassemblies rotate automatically for access. Robotic arms position heavy components with millimeter accuracy. Gravity is managed by machines. Unlike ZIL's overhead chains, movement here is enclosed and guided. Cylinder heads are lowered vertically. No manual correction is required. Fastening sequences follow programmed order. Human deviation is removed. Completed engines are lifted and transferred automatically. This is modular production. Each unit is identical by design. ZIL relied on interchangeable parts. UAZ relies on interchangeable data. Engines exit the cell ready for integration. This is a departure from ZIL's long manual lines. Here, structure is formed in minutes. Quality control is embedded inside the process. Inspection is no longer a separate stage. Robots pause automatically if deviation is detected. Production stops itself. Finished body modules are transferred downstream. This is modern industrial discipline. Precision is enforced by code. Body shells and powertrains approach final integration zones. Separate flows converge. Compared to ZIL, the workforce is smaller. The system carries the load. Where ZIL emphasized endurance through mass, UAZ emphasizes accuracy through automation. The result is a different philosophy of production. Less visible effort, tighter control. Next, the evolution continues, from automated assembly to modern commercial vehicles, as production shifts to the Valdai truck line. The Valdai assembly hall opens as a single continuous volume.
Let's turn on.
Robotic stations replace segmented workshops. Production capacity is defined numerically. Up to 45,000 trucks per year. Industrial robots enter the line. Their task is repeatability, not improvisation. Toolheads change automatically. Cab shells move on synchronized carriers. Inside the cab structure, access corridors remain open. Weld points are counted in the thousands. Surface geometry is checked visually and optically. Completed cab shells enter light tunnels. Multiple cabs move in parallel. Uniformity replaces batch variability. Unlike ZIL-era lines, correction is not expected. Errors are prevented upstream. Coordinate measuring machines scan reference points. Deviation is measured in fractions of a millimeter. Inspection probes touch control holes and seams. Results are compared to digital masters. Cab geometry is approved before painting. Rework loops are minimized. An operator supervises data, not tools. Human control shifts from hands to screens. Surface preparation begins with washing and phosphating. Corrosion protection is applied chemically. Electrophoretic coating covers internal cavities. Areas unreachable by hand are fully sealed. Primer application follows automated paths. Thickness remains uniform across panels. Paint robots spray without pause, no variation in distance or angle. In the ZIL era, paint followed assembly. Here, finish precedes integration. Oven curing stabilizes the coating. Thermal cycles are computer-controlled. Before final assembly, seams are sealed. Manual application remains, but within strict templates. Sound insulation panels are installed. Noise reduction is engineered, not incidental. Paint quality and seal continuity are confirmed. A dashboard module sits ready. Assemblies arrive pre-built to reduce line time. The full dash is moved in as one unit. Connectors and harnesses are standardized.
Cozy just like home.
The module seats into the cab opening. Long beams are staged on low carts. Material feed stays close to point of use. Workers fit components to the frame. Manual work remains, but it's guided by fixtures. 2 technicians work the same station. Parallel labor shortens cycle time. A frame section is lifted. Rigging provides controlled rotation and safe access. The harnessed structure pivots. Alignment is prepared before final fastening. The camera shifts to the line path. Stations are arranged for predictable motion. A close view of couplings and lines. Routing is neat to prevent abrasion failures. A digital readout appears. Torque is measured, not estimated. A tool engages a joint. Tightening is logged and repeatable. Close on a pivot point. Fasteners are secured at defined angles and loads. Anti-corrosion coating is applied. Coverage targets high-exposure surfaces. The underside is shown. Layers protect seams, brackets, and welded edges. A wide front view appears. Cab integration is imminent. A station control panel sits beside the line. Wheel fasteners are tightened with multi-spindle tooling. Uniform torque across studs. The front grille is shown. Final appearance arrives after structural proof. The completed unit moves to automated testing. Verification becomes its own line. Rotation and fastening integrity are reconfirmed. ZL relied on interchangeability. Valdai relies on measurement, torque data, and controlled environments. Next, we scale up again. Mercedes Actros assembly, where automation and logistics run at a higher volume class. The Actros assembly begins with full plant logistics. Production halls are organized for parallel cab and chassis flow. Interior modules are installed before drivetrain integration. Overhead cranes coordinate cab rotation and transfer. The engine module arrives fully assembled. Cooling, intake, and accessory systems are pre-mounted. Alignment occurs using fixed reference points on the frame. Interior panels and driver interfaces are installed. Electrical looms are routed along predefined channels. Cab doors are mounted and adjusted inline. Gaps are measured before progression. Unlike ZIL's static assembly halls, movement never stops here. Exterior components are verified visually and digitally. Brand elements are installed manually. A quality operator confirms completion via digital checklist. Undercarriage inspection verifies drivetrain alignment. Leaks and vibration are unacceptable variables. The finished Actros advances under full illumination. Exterior lighting functions are tested sequentially. Cab sealing is verified through controlled environment checks. Production responsibility ends here. Compared to ZIL's mass rigidity and Valdai's hybrid automation, Actros production is fully system-driven. Every operation is logged, traced, and repeatable. Human labor executes, but software decides. Next, this logic evolves further. The same line adapts to electric propulsion. E-Actros. The E-Actros line operates inside a fully integrated Mercedes production campus. Logistics, assembly, and testing are digitally synchronized. The electric power platform replaces the combustion drivetrain. Battery carriers and e-axles define the chassis layout from the start. Overhead conveyors move modules, not loose components. Each carrier follows a predefined tacked window. Unlike ZIL's manual driveline fitment, alignment here is software verified. Workstations are shared between technicians and automation. In contrast to Valdai's mixed manual process, the E-Actros relies on traceable closed-loop fastening. Electrical connectors are checked visually and electronically. Cab shells arrive pre-wired and pre-trimmed. Only final interfaces are connected on the main line. Technicians connect control units to the vehicle network. Software initialization begins immediately. The E-Actros badge is installed after electrical validation. Branding follows functionality. Movement on the line accelerates as subsystems come online. The vehicle transitions from assembly to commissioning. This phase replaces mechanical tuning with software calibration. a fundamental break from ZIL-era production logic. Only after successful commissioning does the truck exit assembly. The E-Actros enters the test lane under its own electric power. High-voltage systems undergo isolation testing. Leakage thresholds are strictly defined. Engineers monitor data from a control room. Testing is supervised remotely. Cold weather testing footage confirms real-world performance. Electric drivetrains operate without warm-up. Snow and low traction conditions test control algorithms. Traction management replaces mechanical locking. High-speed stability is evaluated under load. Energy consumption is logged continuously. Interior systems are checked for user interface response. Charging ports and connectors are tested under load. Cycle life is simulated, not assumed. Compared to ZIL's mechanical endurance, this truck proves itself through algorithms and sensors. Next, Mercedes applies this platform to extreme conditions: off-road, heavy-duty, and terrain-focused trucks. Production begins with the off-road ladder frame placed on a fixed assembly stand. Operators position the frame using mechanical supports and lifting straps. Cross members are positioned manually. Each joint is seated carefully before fastening. Fasteners are installed progressively. Torque is applied in stages, not in a single pass. Operators pause frequently to verify alignment. Nothing advances until geometry is confirmed. This pace contrasts with historic ZIL lines, where frames advanced continuously regardless of local completion. Here, progress depends on correctness, not speed. A cab-based structure is introduced directly onto the prepared chassis. Cab construction begins on the frame, not on a separate line. The cab floor section is aligned over mounting points. Final positioning is guided by hand. Fasteners secure the cab base to the chassis. Load paths are established before vertical structures are added. Workers move around the structure, not the other way around. The vehicle remains stationary throughout. Additional cab floor components are installed. Each element is fitted, checked, then fixed. This marks the transition from pure chassis to vehicle structure. At ZIL, cab and frame often progress together along conveyors. Here, integration happens in place. The cab enters the paint process. Color coverage is built layer by layer. After painting, the cab returns to the assembly environment. Finish quality is immediately apparent. This step replaces raw metal with identity. Glazing is handled manually. The windshield is positioned by hand and guided into the aperture. Seal contact is checked along the perimeter. No robotic applicators are visible. Fit is confirmed before release. At ZIL, glazing followed a fixed conveyor rhythm. Here, the cab remains stationary until fit is correct. Small metal components are prepared at bench stations. Parts are deburred, checked, and staged by hand. Nothing moves forward unverified. This is low automation by design. The process favors adaptability over speed. Workers access components from multiple sides. Chain hoists control vertical movement. Loads are balanced manually before engagement. There is no automated centering. At ZIL, engines dropped into frames by repetition. Here, alignment is slow and deliberate. Clearances are checked continuously. Hands, not sensors, control final positioning. Fasteners are installed in sequence. Torque tools are handheld. Geometry is locked only after visual confirmation. Multiple operators work simultaneously. Each controls a defined zone. Accessory drives are installed manually. Belt routing is checked by sight and feel. Hoses and lines are secured individually. Electrical connections are joined one by one. There is no centralized harness drop. Verification is tactile and visual. This contrasts sharply with ZIL's linear simplification. The completed cab is lifted as a single unit. Overhead cranes control descent. Operators guide the final centimeters. Cab mounts align with the chassis. Fasteners are tightened progressively. Load is distributed evenly across mounts. Only after fixation does the structure become one vehicle. Exterior panels are installed manually. Grille and branding are applied by hand. Visual alignment defines acceptance. Wheel loads are applied under controlled conditions. The system simulates real mass. Braking force is measured statically. Suspension behavior is observed, not calculated. Data appears, but judgment remains human. Testing continues beyond the factory floor. This is off-road production by restraint, not speed. Next, scale changes again. From specialized off-road builds to Daimler Trucks production, where volume reshapes discipline. Daimler Truck's production begins with body components entering automated framing stations. Structural welds are applied using programmed resistance and arc welding systems. Cab shells move into corrosion protection, passing through multi-stage cleaning and e-coat baths. Electrodeposition ensures uniform coverage inside enclosed structural cavities. After curing, the cab enters surface preparation and paint application. Painted cabs transition to trim and final assembly lines. Interior modules, wiring harnesses, and insulation panels are installed in sequence. In parallel, chassis assembly progresses below. Axles, suspension systems, brake lines, and fuel tanks are mounted to the frame. Powertrain modules arrive pre-assembled. Engines and transmissions are aligned and lowered using synchronized lifting systems. The cab is then married to the chassis. Precision locating pins ensure exact interface alignment. Final stations focus on quality verification. Torque values, electronic systems, and safety components are checked and logged. Compared to earlier manual truck assembly, automation increases repeatability and throughput. Yet skilled technicians remain critical at inspection and calibration stages. This completes Daimler Truck's production flow. Next, we move to a different philosophy of scale and speed: Chevrolet Silverado HD production. Production begins in the body shop. Pre-stamped steel panels enter automated framing cells. High-precision spot welding locks geometry in place.
Laser on.
This forms the body in white, or BIW. Completed body sections move into inspection cells. Structured blue light scanning maps each panel surface. The verified BIW proceeds on automated carriers. Each unit receives a unique digital tracking ID. Scanners monitor progress through every production zone. The body enters the electrocoating process. BIW shells are fully submerged in primer solution. After coating, the BIW enters inspection tunnels. Trained technicians inspect seams and panels by hand. Any defect is corrected immediately. This hybrid approach marks a key difference from early truck production. Modern quality control combines sensors with skilled labor. Bodies enter sealed paint rooms. Robotic arms apply primer with synchronized motion. Rotary bell atomizers distribute paint evenly. Paint quality defines both appearance and durability. Painted bodies are visually inspected. Gloss, color uniformity, and finish are evaluated. Finished bodies move via conveyor systems. Technicians perform final touch inspections. Hands detect irregularities machines may miss. This step remains essential despite automation. From quality control, bodies enter general assembly. Wiring harnesses, insulation, and interior structures are installed. The Silverado HD cab is lifted by robotic handlers. High-load capacity equipment manages the vehicle's mass. In parallel, the powertrain is prepared below. The cab is lowered onto the chassis. Mounting points align precisely. Bolted connections secure the structure. Suspension components are attached. Axles and driveline parts follow. Wheels are installed to allow rolling movement. The vehicle becomes mobile on the line. Front panels, bumpers, and lighting systems are added. Electrical systems are tested immediately after installation. Fit and function are verified. Completed trucks enter dynamometer stations. Engines are run under controlled load. Each Silverado HD is signed off digitally. The truck is released from the line. The completed Silverado HD leaves the factory. This is how heavy-duty trucks are built today. From digitally scanned body shells to robotic assembly. Next, we shift to a different philosophy and another approach to truck manufacturing. Next, Ram Trucks assembly. At the Sterling Heights assembly plant, production begins with automated chassis handling. Robotic arms stage the frame and suspension mounting points. Powertrain module arrives as a pre-assembled unit. Engine, transmission, and driveline are integrated before marriage. Parallel to chassis work, the cab body advances on a separate conveyor. Interior components are installed before body marriage. Dash carriers, HVAC modules, and wiring harnesses are pre-aligned. Operators use pneumatic manipulators to handle large interior modules. These tools stabilize parts and reduce assembly variation. Human input remains critical, but assisted by precision equipment. Cab is then conveyed toward final body-to-frame marriage. Automated carriers synchronize cab height, angle, and speed. This process replaces the crane-based methods of earlier generations. Body and chassis are joined in a single controlled motion. The assembled truck moves to wheel and suspension stations. The completed truck enters dynamic inspection zones. Operators visually inspect body panels under controlled lighting. The finished vehicle exits the line under its own power. Where ZIL relied on labor and adaptation, RAM relies on systems and precision. Next, we move to Ford Super Duty production, where scale, payload engineering, and heavy-duty assembly take center stage. In the stamping facility, large steel sheets are fed into high-tonnage presses. Body panels for the Super Duty are stamped with extreme dimensional accuracy. Robotic handlers transfer finished panels downstream. Completed cab shells are inspected for alignment and weld quality. Large dashboard assemblies are positioned using ergonomic assist tools. Primary wiring harnesses are routed through predefined channels. Harness clips secure cables away from heat and vibration zones. Panels conceal wiring while allowing future service access. Adhesive is applied to the windshield perimeter. Robotic systems control bead thickness and placement. In a separate area, the chassis and powertrain are built simultaneously. Suspension components are assembled for load capacity and durability. Axles, springs, and braking systems are installed. Each step follows a fixed mechanical sequence. Robotic systems assemble transmission housings. Components are measured and verified during installation. Dimensional data is recorded for quality traceability. High dexterity operations are completed by skilled technicians. Precision assemblies require human control and inspection. Assemblies are checked against digital work instructions. Valve bodies are assembled in clean room conditions. Sequential assembly ensures hydraulic integrity. Contamination control is critical at this stage. Completed transmissions are staged for vehicle integration. Automated guided vehicles transport assemblies across the plant. Movement is synchronized with vehicle build order. Engines and transmissions are joined to form the powertrain. This assembly is verified before vehicle integration. The cab is lowered onto the rolling chassis. Front grills, lighting, and trim are installed. Completed trucks are driven under their own power. Where older trucks relied on manual assembly and limited verification, modern Super Duty production integrates robotics, data, and precision. Strength is engineered, measured, and validated at every step. And beyond structured assembly lines, the next evolution removes the driver entirely. This leads into autonomous truck systems. Trucks were once guided entirely by human judgment. Today, that role is increasingly shared with sensors, software, and artificial intelligence. Autonomous systems combine cameras, radar, and LiDAR to perceive the road in real time. Algorithms manage steering, braking, and routing with millisecond precision, from manual control to supervised autonomy. This is not science fiction. It is the next operational step in heavy-duty transportation.
Thank you for watching. Subscribe, share, like.